Hello again everyone, welcome back to ptet.chemistry channel. So my name is Dr. Ont, and in this tutorial video I'll go through this restructured format kind of A-level chemistry tutorial for the Cambridge International 9701. This is for the June 2021. Is a recent summer 21 exams. This is a paper 4 variant 2, so it's one of those really long tutorial as a result of it being my line is not straight, I beg your pardon. Yeah, it's one of these really long tutorials in paper 4 where I actually think out loud and I try to go through concepts that are not just directly what the question asks, but also the associated or the related concepts that I think are relevant and important recap for you or for anyone else who are watching this tutorial video, I guess. So if you think it's too trivial for you, just feel free to skip on to the next question. But if you feel they are useful, then at least by not going through all the tutorial videos, but by going through just selected ones, you will still be picking out useful things along the way. So that's the whole purpose of my tutorial videos, where I focus more on the learning and rather than just doing the exam paper itself. And for that you have the marking schemes and you have many other resources to refer to. Okay, so before I do get started, so make sure you support the channel by clicking the button on this bottom right. To subscribe to the channel is entirely free, and to get notifications and updates, so do turn on the bell button, and follow me at ptet.chemistry on Facebook, Instagram and Twitter to get connected, to send in questions, messages of your achievement, your struggles. Look forward to hearing from you. Okay. So let's get started. In this question 1, so this is a transition metal chemistry. So they first wanted us to do this electronic configuration of this gaseous ion. So it's more like a AS level question. Before you do that of a transition metal ion, you should try from the atom first. So I'll do chromium atom. Chromium atom from the periodic table, I start off from this simplified argon notation. So there is up to argon, and then I fill out the 4th row of the periodic table. So there's potassium and calcium, so it's 4s2. You count the element in the D block: scandium, titanium, vanadium, chromium. So it looks like 3d4, and this is actually wrong from your AS chemistry because they repel more. When you put the 2 electrons in the S subshell, it's much better if you promote one to the D subshell. At least then they are occupying each of the D orbitals individually and pointing in their own directions, such that they repel lesser. The electron repel lesser, so this is favored, this is slightly more favored, and this is the adopted configuration for chromium atom. The other case where this also appear is in the copper gaseous atom. Copper atom without any electrons having been lost. It's copper being argon 4s1 3d10. Okay, now we fill 4s before 3d, but we also lose from 4s before 3d for the transition metals. So what happened then is I lose one there, I lose my second one there, and then I lose my third one there. So if they ask for chromium 3 plus, which is what the question is asking, chromium 3 plus, I'll have argon, I'll have 3d3 because I lose the first one, and then I lose 2 more from there, so 5 minus 2 is 3. But of course they want us to complete the electronic configuration in the complete manner. So 1s2, 2s2, 2p6, 3s2, 3p6, and then 3d3. That would be the correct configuration for Cr3 plus ion there. A part 2, they want us to define what is meant by complex ion. So it's an ion, so it's an ion formed by ligands connecting or bonding to, forming by ligands, forming dative covalent bond, or you might call it coordinate bond, whichever one you like. Just stick with one form or the other. So forming dative covalent bonds or coordinate bond, as I mentioned, to the metal ion center, So essentially when you have a complex, you have ligands, you have a metal center, and these ligands form covalent, dative covalent bond to this metal ion center. Then we call them as complex. Part B, so question 1, part B is about, they say it shows similar reactions or similar chemical properties as cobalt chemistry. So chemistry of cobalt 2 is actually in your syllabus together with chemistry of copper 2 plus. So you should really know them very well. So we have NaOH, which is just acting as a base, OH minus. We have H2O2, which can act as oxidizing agent, and we have NH3, which can act as both initially as a base, and then in excess is going to be a ligand. So in terms of the reagent added, and then we have to describe the formula. Well, we have to get the formula of the chromium species form, and we have to identify the type of reactions. So we are not being asked for any equations or whatnot here. We're just being asked on, well, what happened in each case. First of all, you have NaOH aqueous. So this is the source of hydroxide. Hydroxide precipitate out the cobalt as cobalt 2 hydroxide, and that is like, it started from this solution, which is kind of like a pink solution. So they haven't asked us to describe the color of these things with the chromium species, because the chemistry of chromium compounds are not specified in your syllabus. But of course, we know that the cobalt species were in the presence of NaOH. I think I better move this table to a new page, because I want to talk a lot more about this than the space given. So what happened then is the cobalt species, if I do NaOH aqueous, I'll get a cobalt 2 hydroxide, and this is a blue precipitate. And if I have H2O2, we know that we get this disgusting brown solution where the cobalt actually get oxidized to cobalt H2O6, but now it's 3 plus, because it's the oxidation of the cobalt 2 to cobalt 3. Actually, I beg your pardon, it's not a brown solution. You get the brown solution when you try and oxidize the cobalt with 6NH3 with a 2 plus into the cobalt with 6NH3 and 3 plus. I actually don't know the color of this cobalt 3 plus aqueous solution, but I know you will oxidize the cobalt 2 to cobalt 3 using the oxidizing agent. In the presence of excess NH3, you're going to get cobalt NH3 6, 2 plus. And that, just like what I said, when you add in the hydrogen peroxide, it does go to like brown or much darker brown kind of color. So it's quite a disgusting color, unlike the very nice color that we usually see with transition metal complexes. They're not asking for color here because these are associated with the chromium compound. But thinking about the relationship between what happened there, we can deduce the formula of the associated chromium compound. But be careful, these are cobalt 2 complexes. We are dealing with chromium with 6 water, and we have a 3 plus there. So our formula of our hydroxide will be chromium with 3 hydroxide, because it cancels out the charges of the 3 plus on the chromium. And this is a precipitation reaction, because what we are doing is we are precipitating out the chromium 3 hydroxide. Back in year 9, you will be expected to write half equation. Sorry, not half equation. What am I talking about? Ionic equation. So chromium 3 plus, which of course is actually chromium H2O 6, and then 3 plus. So there's your aqueous. I'll add in 3 aqueous hydroxide ion, and I'll kick out chromium hydroxide as your precipitate, as your solid. And then I'll also kick out the 6H2O. So this is ionic equation for that precipitation reaction there. Okay, so to the next one, which is H2O2 aqueous. So this will be, it could be oxidizing or reducing agent in the context of chromium 3 plus. So we know that will actually go to chromium 6 plus. If you look at the E0 value, so chromium plus 3 in the chromium 3 plus aqueous. If you want to go to a higher oxidation state, of which it is stable one, you just have to look in the data booklet. You don't have chromium 4, you don't have chromium 5, you have chromium 6. And examples of chromium 6 you will have come across as Cr2O72 minus, which is your orange color. But of course, they are in equilibrium depending on the acidic or the alkaline conditions that you have. With this chromate 6, this is also chromium plus 6, but this is yellow in color. This is called chromate 6, whereas the other one is called dichromate 6. Okay, you might not have seen the equation before, or you might have. Pardon me, I might actually get this wrong the first time, but let me just try and write the equation first. So it's a very common equilibrium questions with Le Chatelier principle in AS. So I got 2 chromium, I got 8 oxygen, I got 7, which means the H plus is on the right hand side, and I have H2O on the left hand side. That way I just have like that, and I've got the 7 plus 1, 8 oxygen. I've got the 2 hydrogen, I got the 2 chromium. So this equation is a balanced equilibrium now. So this is your yellow color on the right, this is your orange color on the left. This is a very common question. Is it a redox or is it not a redox? Back in AS, they can ask you in terms of Le Chatelier principle, the color changes as you add in more acid. As you change the acid, all acid contain H+, so it shouldn't affect the color distribution at all. And all acid will do the job because all acid contain H+. The other question they can ask is what happened when you add in hydroxide? Hydroxide can change H+, and therefore they can change this concentration of H+. As they neutralize the H+, they can make this equilibrium shift to one side, and therefore you can get different color. Anyway, going back to the species of the chromium that you're going to get, has to be chromium plus 6, so you can get Cr2O72 minus, which is dichromate 6. If you want, if you know your other chemistry, you can write down Cr042 minus as well, but I will bet that Cr2O72 minus is probably something that you are very familiar with. It is actually the oxidation of the chromium species from chromium plus 3 to chromium plus 6, but it's a reduction of this species. So instead of writing oxidation, I am happier to write redox because you have a partner in oxidation, chromium plus 3 to chromium plus 6, and then you have the H2O2 that undergo reduction. I haven't shown you where to get a chromium plus 6, but I hope you know where to get it. Maybe I should quickly just show it. Chromium plus 6 oxidation state. So if you have Cr2O72 minus, don't know why I write it down, minus 2 overall charge, 2 chromium plus 7 times minus 2. The oxidation state of each oxygen, the compound is minus 2. So 2 chromium is plus 12, each chromium is plus 6. For the Cr042 minus, the charge is minus 2, so that's the overall oxidation state. Chromium plus 4 times minus 2, chromium is going to be plus 6 there as well. No change in redox, no change in oxidation number. This is not a redox equation. Moving on to the very last part of this question. So you have excess of NH3. With a little bit of NH3, it's going to behave just like hydroxide because NH3 is a base. So initially you get a precipitate of chromium 3 hydroxide. Just like with the cobalt, with a little bit of NH3, you initially get this blue precipitate. When you add in excess NH3, you get this brown solution forming. Essentially what we have is going to be this cobalt. Oh, sorry, not cobalt, because we are not talking about cobalt chemistry. Chromium with not H2O, but NH3. It's going to be a complete substitution, so 6 of them. And then this one will have a charge because this thing has no charge as a ligand. This is not a redox reaction. It's just substituting the H2O, the 6 H2O with 6 NH3. So I still maintain the 3 plus charge, which I have got in my chromium 3 plus aqueous solution, which by the way is green. So that is what you call chromium 3 plus aqueous, and that is the color you get when your dichromate 6 act as oxidizing agent. They go from orange to green. This is the green color of that aqueous chromium 3 plus. So that is just your classic ligand substitution reaction because you're just substituting one ligand with another, and this ligand is the same as H2O in the sense that they are both uncharged, zero charge ligand there. Question 1, part C, is basically this idea of, it's not really our fixed essay, this is slightly different, but they are talking about why different ligands, different colors. So it's not really about the origin of colors, it's more about why are there different colors when you have chromium H2O6 with the 3 plus versus this chromium 2 O2CCH3. What is this thing here? But anyway, doesn't matter. So why? Okay, the two complexes have different ligands, have different number of H2O ligands. So on the left you have 6 H2O, on the right you just have 2 H2O. So overall different ligand set meaning different combinations of ligands in the complexes. We know that the d orbitals actually get split, as you know, in the presence of ligand. The d orbitals get split like that in the octahedral complex, whereas they don't get split without any ligand at all, without ligand. And this splitting is separated by delta E equal to HF equal to HC over lambda absorb. And they can only absorb in the visible light region, and therefore whatever color that you see has to be the combination of the colors that are not being absorbed. So the fact that we do get splitting is a result of the repulsion of the ligand and the d orbitals that contain the electrons. So they repel differently, giving you different energy gap. So therefore this ligand, different ligand sets, therefore different repulsion between ligands and the electrons in the d orbitals. Therefore different delta E equal to HF equal to HC over lambda absorb. That means different lambda absorb for the visible light. If you absorb different lambda, if you absorb different wavelength of the visible light, therefore we see different complementary color. So different complementary color. So this is a very very much waffling, but you know it still need to involve the right concept, different complementary colors observed. So it's just about the different delta E. I think that is the main concept there. They're not even asking you to draw this splitting diagram or whatever, but for that 2 marks I would say the idea is different ligands, different repulsions, different delta E, different lambda absorb, different complementary color absorb there. Okay. Question 1, part D. So we are given this thing here. So they purposely, well, they went away and tell you water and ethanoate ions behave as different type of ligand. So H2O is a monodentate ligand. Monodentate ligand means they only form one dative covalent bond per water molecule, only forming one dative covalent bond per ligand molecule. So per ligand, ethanoate ion, which is basically CH3CO2 minus, like that. So they have got 2 sides there. So first side is on this oxygen, but these electrons can get delocalized over the carbon sp2 framework there. So ethanoate ion acts as a bidentate ligand. Bidentate ligand basically means they can form 2 dative covalent bonds per ligand, forming 2 dative covalent bonds per ligand, and this is not ligand molecule per ligand ion there, because ethanoate ion is an ion. Now deduce the coordination number of chromium and the geometry in this structure. So the structure they have given you is like that, and then they have got the OH2 there, and they have shown this is pointing out, and this is pointing away from you behind the screen. And I've got O and O there. There is 1, there is 2, and then if I just draw there on top and on top like that, there's 3, and below there is 4. Okay, so I have 4 of these ethanoate ions, and I want the coordination number. So first of all, coordination number refers to the total number of covalent bonds. Total number of dative covalent bonds. Coordination number is the total number of dative covalent bonds around a metal center. So I have 1, 2, 3, 4, 5, 6. I have an octahedral environment. So 6 dative covalent bonds around my 1 chromium center. My geometry is octahedral. My bond angle is 90 degrees for each of these things there. What is the type of bond between the chromium and chromium? So that is going to be a covalent bond. So it's quite rare that you think about metal forming covalent bond, but in this case, each of these is a dative covalent bond. So this has got to be a covalent bond being shown as such there. So there's just covalent bond between the chromium atom there. So question 1, part E. So we're going to construct an equation. So this is a little bit of electrochemistry. We have Cr2 plus oxidized to Cr3 plus. So we have Cr2 plus aqueous going to Cr3 plus aqueous. That is based on the question. And in doing so, this chromium plus 2 to chromium plus 3. So I must lose electrons. That is my oxidation. From your O-level or IGCSE chemistry, there was an acronym. Oxidation is losing of electrons. Reduction is gaining electrons. So I've lost electrons. I have the electrons on the right hand side from the lower oxidation state to the higher oxidation state. So I react with oxygen. So I need to find something where the oxygen undergoes reduction. So oxygen has to gain electrons. I found it in the data booklet. O2 plus 4H plus 4 electrons going to 2H2O, and this is my reduction. So I just write oxidation there, and this reduction because gaining of electron, the other one is loss of electrons. If I just write down the E naught, basically the standard reduction potentials for the second one is plus 1.23 volt. And for the first one, it's obviously being shown as reduction potential. So you're looking for chromium 3 plus going to chromium 2 plus. So there's minus 0.41 volt. This is as given in the data booklet. It's shown for the reduction, which is going this way, chromium 3 plus plus electron going to chromium 2 plus. But we have identified that as our oxidation. So this is our E-ox and this is our E-red. So going back to your thing there, they want you to write an ionic equation. So we need to write where the changes in oxidation number get balanced out. This is 4 electron, this is 1 electron. Lowest common multiple, primary school mathematics, says that you must come up with a common factor there. So common factor there is 4. So multiply this whole thing by 4. Then you're going to get 4, 4, and 4. The 4 electrons on the right cancel the 4 electrons on the left. But what you get is O2 plus 4H plus, and then you have 4 Cr2 plus going to 4 Cr3 plus 2H2O. They come from this balance equation, which we have gotten straight from the data booklet. We've done our multiple of 4 correctly. The 4 electrons cancel out, so everything should just balance out. O2 to oxygen, 4 hydrogen, 4 hydrogen, 4 chromium, 4 chromium, plus 4. And then plus 8 is plus 12, plus 3 times 4 is plus 12. This equation is definitely correct. Last but not least, they want us to do in part 2, calculate the E cell for this reaction. E cell is E red minus E ox. So this minus already take into account that the E ox is the opposite step. So this is what we have written down straight from the data booklet. It was shown for the reduction potential. I identify this as my E-ox already. I do not change the sign whatsoever. I just do my E red plus 1.23 minus, and then minus 0.41. As I said, I do not change the sign. I just take it as it is from the reduction potential, showing the reduction from the data booklet. And ultimately, I put that into my calculator, 1.23 minus 0.41 negative. I get 1.64 in my calculator. That would be wrong, because as with anything physical chemistry, sign, value, and unit are very, very important. And as you could see, this is greater than 0. So the E cell is greater than 0. So this is feasible, and this is spontaneous reaction, and this will happen. That's why chromium 2 plus aqueous will get oxidized in air to chromium 3 plus, which will give you the green coloration if you just leave it in air naturally. That's the end of that 15 mark first question on transition metal chemistry.